Buffered solutions are solutions that resist changes in pH. A solution that resists a change in pH are known as buffered solutions. Solutions that can have strong acids or strong bases added and not have their pH change have been buffered. We see either a weak acid and its salt, or a weak base and its salt creates a buffer. Notice that I have said they must come from weak acids or weak bases. That eliminates any type of buffered system coming from strong acids or strong bases. And we can make a buffer for any pH by simply varying the concentrations of these solutions. In our question, it asks us to consider which of the following conjugate acid-base pairs would not function as a buffer. Keeping in mind, buffers must come from weak acids or weak bases. So buffered systems must be made from weak conjugate pairs. When I look through our choices, it says HCOOH going to its conjugate base HCOO negative. This is the ionizing hydrogen. It is not one of our 7 strong acids, therefore, yes, this set of conjugate pairs would form a buffer. Bicarbonate ion and carbonate ion are conjugate pairs. They differ by only one hydrogen ion. Neither is coming from a strong parent, so yes, that conjugate acid-base pair would function as a buffer. However, nitric acid and its conjugate base nitrate comes from a strong acid. This would not work in terms of functioning as a buffer. So, to answer our question, it's the last one that would not function as a buffered system. Nitric acid is strong and therefore would not work to buffer a solution. Let's consider how buffers work. If a buffer is composed of a weak acid and its conjugate base coming from the first name of a salt, the conjugate acid HX and one of its salt MX. Notice from the last lesson we have a common ion. In terms of a weak acid, it would be the anion. Let's write the dissociation for this weak acid. If HX, representing just general formula for any weak acid, dissociates, it would produce the hydrogen ion and its anion called X negative. If we write the corresponding acid dissociation expression, its products over reactants, we would find that the Ka is found by multiplying the hydrogen ion times the negative X ion all over the value of the molecular form of the acid, HX. Ka represents the ions over molecules, the dissociated over the undissociated form of our acid. If we simply rearrange, solving for hydrogen, naming the same equation, just putting hydrogen equals, so manipulating with algebra to make hydrogen ion, it would solve out to be the Ka times HX all over the X negative. The HX represents the molecular form of the acid, and the X negative represents its conjugate base. We have manipulated Ka equal to H plus times X negative over HX and just solve for hydrogen ion, placing it to the left of the equal, and what happens? We have Ka multiplied by HX divided by the X negative. Simplifies algebraically our formula. We'll need to flip our page in our notes. So it asks, what do we have? If H plus and therefore pH are determined by 2 factors, we could see the value of Ka playing a role, the value of the weak acid has its own unique Ka value, and we also see a ratio of the conjugate acid-base pair, HX over its conjugate base, X negative. And again, that's just simply coming from rearranging the original Ka equation. So from our previous page, if the hydrogen ion can be found by knowing Ka and the conjugate acid-base ratio, we could see two factors affecting the pH of our solution. The pH could be affected by the magnitude of the Ka, and it could be affected by the ratio of the concentrations of the acid to its conjugate base. So, as long as we have this ratio of Hx to X negative, the acid to its conjugate base, if it's very large compared to the amount of hydrogen or hydroxide we add, the ratio doesn't change much, and thus the change in pH is quite small. So Ka is a constant, we can't change that, but we could add to a solution large amounts of the conjugate pair of Hx and X negative so that they are there ready to absorb excess amounts of acid or base. Let's give it some thought. What happens when sodium hydroxide is added to a buffer composed of acetic acid and its conjugate base acetate, knowing that the acetate ion would have to come from one of its salts, perhaps sodium acetate or potassium acetate. We do need a source of the negative ion, generally coming from some salt. So if we have a buffer system consisting of acetic acid and acetate, NaOH is a strong base. Knowing that we have an acid and its conjugate base, if we pour in sodium hydroxide to a system that's buffered, and the buffer is the acid and its conjugate base, we would recognize that NaOH would react with the acid portion of the buffer. NaOH with acetic acid would provide us, and again just a double displacement, with NaC2H3O2 and water, HOH. Now thinking this through, the driving force here, the sodium ion of course acting as a spectator, we could also write that in terms of a net ionic equation. When a base is added to a weak acid, I'm seeing an increase in the amount of acetic acid's conjugate base, whoops, that's a -1, and water. C2H3O2 -1. I'll repair that best I can. C2H3O2 -1, the acetate polyatomic ion. So all we've done is eliminated the sodium as a spectator. When a base is added to a buffered system, the acid is there waiting to help absorb the excess amounts of hydroxide being added. If I think about this in terms of a bar graph, let's suppose I have equal amounts of the conjugate acid, I'll call Hx, and its base X negative. And in this system, let's just visualize acetic acid in this particular area and the acetate ion in this area. If we were to add strong base, we see that the acid gets consumed and the acetate gets made. Visually, we can show that as the amount in a bar graph of the original value here. Keep in mind, I'm just trying to do a bar graph. If the acetate ion went down, we end up looking something like this. The Hx value is a smaller amount, and the X negative value is an increased amount. Now what I'm trying to show in a bar graph, the added value of acetate to this region here of the original amount should be equal to the Hx value that has been decreased. That the amount X went up is equal to the amount Hx that was consumed. Adding a strong base created more base and less acid. Let's consider what happens when HCl is added to the buffer. The same buffered system, but this time we're adding acid. If HCl is a strong acid and our buffered pair is hydrogen acetate and the acetate ion, acid reacts with base. Let's consider HCl, and again, let's just write the net ionic and I'll eliminate the spectator chloride. So HCl will be represented as H+. We'll add that to the base, the conjugate base, C2H3O2 negative. And we could see the formation of more acetic acid. Let's consider in the same bar graph the opposite direction. If I add strong acid, like hydrochloric acid, to a system that's being buffered, and again, HX is representing acetic acid, the acetate is being represented by X negative, a conjugate acid-base pair. If I add more H positive, we saw, in terms of the bar graph, the amount of acid that was produced going up, and again, considering the equal amounts here, the amount of base that was consumed going down. We made more HX and we used up X negative. We made more acetic acid as the acetate was consumed. The amount that HX went up in value is equal to the amount that X negative was consumed. So buffered systems start out equal. And if I add base to a solution, I'm ready to absorb that excess base with the acid. The acid gets used and the conjugate base goes up. If I add to this conjugate pair excess acid, it's the acid value that goes up and the base goes down. Visually, you could see the more conjugate pair, the higher the bar graph here that we start with, the better the buffering capacity of our solution. To calculate the pH of a buffer, we revisit our initial equation for Ka. I remember Ka is equal to the products over reactants. So we have H plus times X negative all over HX, where this is true for any weak acid. We also rearranged to solve for the hydrogen ion and thus pH by showing it was the same as writing Ka times the hydrogen X over X negative, the conjugate acid-base pair. So therefore we see H concentration depending upon the ratio of the acid to its conjugate base, the concentration ratio of acid over base. We could take negative log of both sides, and we do so to turn hydrogen ion into something we're more familiar with, pH. If I find hydrogen ion's value is negative log, that's where the pH comes from. So we'll just simply write pH as the negative log now of hydrogen. And setting this side equal to the negative log of Ka times Hx over X negative, we need to simplify this. Again, negative log of hydrogen ion gave us pH. Negative log of the right-hand side needs to be simplified, and we'll do so by writing pH is now found by negative log of the Ka minus the log of the ratio of the acid over base. Negative log of Ka is known as the pKa. Negative log of the ratio Hx over X negative can actually be simplified to make it a positive log of the base over acid. By flipping that, we get base over acid, and we like to do that to make an addition sign here. pH is equal to the pKa plus the log of the ratio of the conjugate base over its acid. This is a very famous equation for buffered systems, and I believe it actually appeared this year on the AP exam. It's known as the Henderson-Hasselbalch equation. Let's take a closer look at this equation on the next page. The equation we wrote, again, we could write it right here. The pH is equal to the pKa plus the log of the ratio of the base over acid, the conjugate base over its acid. So pH is equal to the pKa, this one here, pH is equal to the pKa plus the log of the ratio of base over acid. That's what I'm trying to denote as A negative for the anion. I just wrote X negative a moment ago. A negative over HA, perhaps you like X negative over HX. What we're referring to is the conjugate base acid pair. Again, this is a very famous buffering equation. It has a title after two gentlemen, Henderson-Hasselbalch, H-A-S-S-E-L-B-A-C-H, the Henderson-Hasselbalch equation. Using this equation is quite easy. Developing it once for the algebra was a little bit tedious, but once we see it, it's now just a matter of plug and chug. Let's try one and show the Henderson-Hasselbalch in operation. It asks us, what is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium lactate? For lactic acid, Ka is 1.4 times 10 to the negative fourth. We could go through the process of using an ice chart, but the key here says that it's a buffered solution. The Henderson-Hasselbalch equation is so much easier. So we simply plug in pH is equal to the pKa, which really is nothing more than the negative log of the Ka provided, 1.4 times 10 to the negative fourth. pKa is negative log of Ka plus the log of the ratio of base over acid. The acid is given to us as 0.12 molar. Its conjugate base is given to us in terms of its salt, sodium lactate. Notice the common ion is the negative name. Lactate is the salt from the lactic acid ion, and its concentration was 0.10 molar. We just simply hit, and I'll grab my calculator. Negative log of 1.4 e negative 4 plus the log of 0.1 divided by 0.12. And when I hit that, I get the pH directly as 3.77 pH units. The Henderson-Hasselbalch equation takes pKa plus the log of ratio of base over acid, where the conjugate base came from the sodium lactate common ion. Preparing a buffer. How many moles of ammonium chloride must be added to 2 liters of a 0.1 molar ammonia solution to form a buffer whose pH is 9? Assume that the addition of ammonium chloride does not change the volume of our solution. Well, let's get a handle of what's going on. We have a weak base, ammonia, being placed into water and setting up an equilibrium with its conjugate acid, ammonium, and the base hydroxide. They give us a Kb value from Appendix D of ammonia, and it was found to be 1.8 times 10 to the negative fifth. This is a base equilibrium, so we need a Kb. Ammonia happens to be listed in that small chart of Kb values found in our Appendix D, and it's the same here, 1.8 times 10 to the negative fifth. All right, so we want to know ultimately the moles of ammonium chloride. Here's what we could start with. Knowing that the pH of the solution is 9.0, that would tell me that the pOH of our solution is 14 minus 9, giving me a value of 5. So the concentration then is 10 to the negative pOH, and that's a value of 1 times 10 to the negative fifth molar. Knowing that, the pH turned into POH and ultimately could be used to solve for the concentration of hydroxide, here's what we now know. The concentration of OH negative, 1 times 10 to the negative 5th molar units. What else do we know? We know the concentration of ammonia was 0.1 molar, so I can record that value right here. Ultimately, we'd like to know the concentration of ammonium to work it into moles of ammonium chloride. So let's set up our equilibrium. Giving the value of 1.8 times 10 to the negative 5th, that would be set equal to the concentration of the ion ammonium times the concentration of the hydroxide ion, which was determined through the use of the pH, 1 times 10 to the negative 5th. We set that over the 0.1 molar, the value of the ammonia given to us in the problem. What we're about to find through the algebra is the concentration of ammonia, which ultimately is the same as the salt we put in, ammonium chloride. So let's hit solving for ammonium. I'll begin by hitting 1.8 E negative 5 times 0.1 divided by 1 E negative 5, and I find a value of 0.18 molar as the concentration for ammonium, which ultimately is ammonium chloride as well. So therefore, we need to find the number of moles, and we're now just ready to use our molarity problem, where the molarity is equal to X moles per liter of solution. We were given a volume of 2 liters, so we just need to cross multiply. The 0.18 times 2 liters would show a value of 0.36 moles of ammonium chloride. In our solution to prepare a buffer, we had a 0.1 molar ammonia solution. What we wanted to know was how much of its conjugate base coming from ammonium chloride, that's its conjugate acid, ammonium chloride produces its conjugate acid ammonium. So we set up our equilibrium problem. Looking at the value of Kb, set it equal to the concentration of ammonium times OH negative, which was determined through the use of the pH, set over the value of ammonia, the 0.1. That gave us the value of ammonium, the polyatomic ion. And then simply cross-multiplying with the volume of 2 liters would tell us to add 0.36 moles of our salt to the ammonia solution to create a buffer. In our last example of preparing a buffer, let's try another one. We'll calculate the concentration of sodium benzoate that must be present in a 0.2 molar solution of benzoic acid, and we want to have it at a pH of 4.00. Let's consider the equilibrium. We have an acid, benzoic acid, HA, all right? And it's in equilibrium with its ions, H plus and A negative. When we look up the value using Appendix D for benzoic acid, Appendix D for benzoic acid shows a value of 6.3 times 10 to the negative 5th. Since this is indeed an acid equilibrium, the pH is truly telling us the hydrogen ion directly. Remember, 10 to the negative pH gives us the hydrogen ion concentration. And so that value would be 10 to the negative 4. We also know the concentration of the acid in the original solution, given to us as 0.2 molar. Let's use our equilibrium to pull out the value of the negative, the A negative, the conjugate base of our acid. So 6.3 times 10 to the negative 5th, the value of our Ka, is set equal to the concentration of the hydrogen ion, which is 10 to the negative 4th, or 1 times 10 to the negative 4th, times the benzoate polyatomic ion, I'll just simply write as A negative, set over the concentration of 0.2, the original acid value. When we solve for the concentration of A negative, that will represent the sodium benzoate. So I'll hit for the concentration of benzoate ion. We would start 6.3 E negative 5 times 0.2 divided by 1 E negative 4. And I find a value of 0.126 molar. Now, we were only asked to go as far as the concentration. Up above, we had to go to moles. So with this value, as soon as I find molarity, that truly is the formula for sodium benzoate's concentration. And that is our answer here. To prepare a buffer, we set up an equilibrium. The salt is then used to determine how much of its conjugate base would need to be added, or conjugate acid if we started with a base, as in ammonia's example. Buffering capacity, our next topic in our buffering lesson, talks about the pH of a buffered solution being determined by the ratio of the base over its parent acid. The conjugate base over acid ratio helps us determine a buffered solution's pH range. When I think of the term capacity, how much can be added to a system that's been buffered before I overcapacitate? In other words, think of this as a sponge. A sponge fills eventually. If I'm pouring in strong acid or a strong base to a buffered solution, it has a certain capacity, a certain amount of acid or base it can absorb before pH begins to swing, but I can overcapacitate if I pour in too much. Just as a sponge holds a certain amount of water, a buffered solution has a certain capacity before pHs go out of whack. So as long as this doesn't change much, the pH won't change much. This ratio of A negative to HA, the base over acid. The more concentrated these two are, the more hydrogen ion and hydroxide ion the solution will be able to absorb. So the larger the concentrations, the bigger the buffer capacity. Oh, and then I wrote that twice. Larger concentrations equal a larger buffering capacity. In other words, in our bar graph, if I have a conjugate pair of an acid and base of this amount, and I compare that capacity to a conjugate acid-base pair in that amount, I will have a larger capacity the more concentrated the buffering solution is. So let's take a look over a pH range, where the pH range over the buffering really acts effectively. So if a pH range over which the buffer acts effectively can be calculated, it's simply by looking at the ratio of Hx when it's directly equal to X negative. Again, visually, it makes sense to have an equal-sized bar graph where Hx is equal to the amount of X negative. This would be the optimal pH range. It would not make sense to create a buffering solution where I have a small amount of one partner compared to the other. This would get consumed much faster than this would. So what we're saying is an optimal pH range is one where we begin with the buffering capacity of equal amounts. Alrighty. The optimal pH of a buffer is when the pH is directly equal to the pKa. And that, again, just simplifies the ratio. So thinking back to an equation we wrote earlier, if H plus can be found, and ultimately pH, by knowing the Ka times the concentration of the acid over base, if this ratio holds those two values the same, Ka and H plus are indeed equal, pKa and H and pH are indeed the same. So this target here, where pH and pKa are indeed the same, gives us the optimal buffer. So try to select a buffer whose acid form has a pKa close to the desired pH. Knowing that a buffering capacity will give us a range of plus or minus 1 pH unit of the pKa. So let's think this through. If the optimal pH of a buffered solution containing acetic acid and sodium acetate, what is that optimal pH? All we would need to do is say the optimal pH is when we have that equal to pKa. So I'll simply take the negative log of the Ka value for acetic acid given to us in the problem as 1.8 times 10 to the negative 5. And that will tell us the optimal pH that this particular series could buffer. And when I hit that, negative log 1.8 times 10 to the negative 5th, I find 4.74. So what that's telling us, with acetic acid and sodium acetate, it is an ideal buffering system that has a pH range within plus or minus 1 unit. So acetic acid with its conjugate base acetate is a buffering system with a pH range of 4.74 plus 1 unit and minus 1 unit. If we think about a buffering system as adding a strong acid or a strong base and determining what effect it has on the stoichiometry. If we add strong acid or strong base in terms of our bar graph, we saw that some of the acid would get consumed or some would get used depending upon what we added. So we have to consider the stoichiometry first. Understand a strong base will grab protons from the weak acid. It will reduce the concentration of the acid. So base plus acid will get consumed. The strong acid will add its proton to the anion of its salt, producing more of the acid and reducing the conjugate A negative. We then use the Henderson-Hasselbalch for our equation. Let's make sense of this with a visual. Let me grab a piece of paper. You might choose to draw this as well, just in a side margin would work fine. Let's suppose I have a buffering system and I have equal amounts of HX and X negative. Perhaps you like to think of HA or A negative, but it's a conjugate acid-base pair. Let's suppose we add strong acid. And we could denote that strong acid with the same symbols as HX. All right. A buffered system comes from a weak acid and its conjugate pair, and we're going to add strong acid to that system. We would understand that the acid reacts with a base. The acid that we're adding reacts with a base. So the base, the X negative from the buffered system, reacts with the hydrogen ion or hydronium ion from your strong acid, forming more acid, HX. When we add an acid to a buffered solution, we produce more of the acid from the buffered solution. Or perhaps to our buffered solution, we add strong base. And we can denote that simply by OH negative, adding a strong base. Consider the stoichiometry of what's happening. A base that's been added to a buffered system will react with the acid from the buffer. So the acid, HX, plus our base, OH negative, allows a proton transfer. X negative forms and neutral water. HX is the conjugate acid from the buffer being added with a strong base. So what's happened? We see a strong base reduces the amount of acid and produces more of the conjugate base. After we consider the stoichiometry, we recalculate. Recalculate the values of Hx that have been produced and the x negative. And now solve for the pH. This little flow chart helps us see visually how to calculate a buffered solution problem. We begin with a known amount of a buffered system, Hx and its conjugate base. We could either add acid and follow that producing more acid, or we could add strong base to produce more base X negative. We'll then recalculate and solve for the pH. This flowchart approach helps us solve buffering problems. So, back to the notepad page. Adding a strong acid or strong base, we consider the stoichiometry first. And that's all I really said in a visual. We're going to consider the stoichiometry to find out how much acid or base is left after we've had our reaction. And then off to the Henderson-Hasselbalch to calculate pH. Let's take a look at a model problem. Calculating pH changes in buffers. A buffer is made by adding 0.3 mole acetic acid to 0.3 moles of sodium acetate. So here's our acid and its conjugate base. So visually, this is the system that we're starting with, 0.3 moles of each, of the acid and its conjugate base. We add it to make a 1 liter solution, which is simply saying the molarity. The pH of the buffer is 4.74 units. So, let's calculate the pH of the solution after adding 0.02 moles of our strong base NaOH. Let's figure out what's happening if we add a strong base, OH negative, to our buffering solution. The base reacts with the acid. Adding the strong base takes us on this journey to consider the stoichiometry. We know that the base ion reacts with the conjugate acid, and in this example, that's acetic acid, HC2H3O2. When we see that, we know that a proton is transferred to give us water, and the acetate ion, C2H3O2 negative. Before our reaction, we had 0.3 molar solution of acetic acid, and we had a 0.3 molar solution of the acetate coming from sodium acetate. We also work out the concentration of the base. The base was given to us as 0.02 molar, so we also have 0.02 molar as the concentration of hydroxide. 0.02 molar, 0.3 molar, and 0.3 molar are before they react. What's left after? Well, let's consider the hydroxide here. Definitely looks like the limiting reagent. It will be consumed throughout our experiment, and reactants get used as products get made. So this goes down by a value of 0.02 molar, giving us a net of 0 molar. It will also consume a value of 0.02 molar from the acid. So after the reaction is complete, we're down to 0.28 molar concentration. We started with 0.3 molar of acetate, but it was made to 0.02 molar additional units. So after the equation, we have a 0.32 molar solution. What we've said is the acid went down in the same amount that the base went up. Once we've done the stoichiometry first, we simply plug it in to the Henderson-Hasselbalch. Alrighty. So pH is found by taking the negative log of the Ka, which for acetic acid we had to look up in Ka value for Appendix D is 1.8 times 10 to the negative fifth. So reminding ourselves of the Henderson-Hasselbalch, the negative log of Ka, 1.8 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base here had a concentration of 0.32 molar, and the acid was reduced down to 0.28 molar. The pH of the buffer is set 4.74. That could be 10 to the negative. 4.74 gave us Ka value then, or we could look it up with Appendix D. The purpose of telling you the pH of the buffer initially, 4.74, is so we can compare what happened to the original pH after we added the strong base. So the 4.74 really doesn't play a role setting it equal to pH. Let's consider, in the same experiment, adding a strong acid to the problem above. So remembering from our original equation, we had a buffered solution where we had conjugate pairs that were 0.3 molar in acetic acid, HA, and 0.3 molar in the acetate ion, A negative. Suppose we wanted to calculate the pH of the original buffer described in the previous problem after adding strong acid, 0.02 molar. So adding strong acid should cause the reaction to change pH. It should decrease on our pH scale. Let's consider if I add acid to a buffered system, the acid reacts with a base, the A negative, and in this case it was acetate. So let's go ahead and show the strong acid as H+, and again eliminating the spectator chloride, reacting with the conjugate base in our buffered system. H+ will react with the base C2H3O2 negative, and it will produce more of the acetate ion. So visually, let's make sense of what we just said. If this is our buffered solution, which we drew a moment ago, and we're adding strong acid, the acid reacts with the conjugate base, producing even more of the conjugate here, acetic acid. Adding strong acid produces more acid in the buffered system. That makes sense. We're pointing at the acetic acid. So let's think about what we know before the reaction. We had 0.02 molar concentration per liter of the hydrogen ion. We had 0.3 molar solution of the acetate, and we had 0.3 molar solution of its conjugate acid. We know that it's all 1:1:1 stoichiometric ratio, so the limiting reagent clearly is the O2 molar H+, and it will use up the reactant and produce more of the product. So let's consider what we have after. Again, reactants get used until they're gone. There will be no remaining amount of hydrogen ion. It also consumes 0.02 molar of the acetate ion, leaving us with 0.28 molar after the equation, and producing O2 molar in addition to the original 0.3, so we have 0.32 molar of the acid. Using the Henderson-Hasselbalch equation, we would show pH can be found by taking pKa plus the log of the ratio of base over acid. So let's calculate pH. Using negative log of the Ka value, 1.8 times 10 to the negative fifth. That value is coming from Appendix D, the value of acetic acid, plus the log of the ratio of base over acid. The base is 0.28 molar. The acid is 0.32 molar. pKa plus the log of the ratio of base over acid. The base this time was a reactant. Let's hit to find the pH of this solution. Negative log of 1.8 E negative 5, close parenthesis, plus the log of the ratio of 0.28 over 0.32, close parenthesis. And we get a value 4.69, if I round, 4.69 pH units. Again, the solution started at about 4.74. It became slightly more acidic, even after the addition of a strong acid. If we were to compare the same thing, adding that same acid to just pure water, we could find its pH directly by taking negative log of the concentration of the hydrogen ion, and we'd hit negative log of 0.02, and that value is quite low. 1.70 would be the pH of that acid in pure water. Adding that same amount of acid to a buffered solution caused the pH to decrease slightly from 4.74 to 4.69. Buffered solutions are conjugate pairs that act as a sponge, soaking up excess acid or excess base, preventing a shift in pH. It changes slightly, but certainly not to the degree if it were in pure water.